There are 11 million children with epilepsy worldwide who experience seizures or dangerous spikes of brain activity throughout their daily lives. Typically, when a child starts seizing, their caretaker will give them medication and the seizure will stop. But for as many as 7% of these children, the seizure can keep going even after, in what is known as status epilepticus, a medical emergency with a mortality rate of 30%, and the most prevalent neurological emergency in childhood, according to the NIH. Status epilepticus is defined as a seizure that lasts longer than 5 minutes or a chain of seizures that happens within 5 minutes. What makes it so dangerous is how difficult it is to detect. Typical seizures are easy to recognize because they usually cause convulsions, where a child's body starts shaking. But by the time a seizure becomes status, the child could be too fatigued to keep moving. So even if they stop convulsing, they could still be seizing. A child recovering from a seizure and a child actively still having one can look exactly the same. Currently, the only way to check if a child is in status is to call their neurologist, describe the situation, and ask. If the neurologist suspects the child is in status, they'll be rushed to a hospital for an electroencephalogram or EEG test to see if their brain signal is irregular. There is currently no way to conduct an emergency EEG test at home, leaving both the child and their caregiver in constant fear that with every seizure, the child could enter status without anyone knowing.
Current devices on the market are either not optimized for at-home use or fail to provide clinical-level signal quality, limiting their usability in emergency scenarios. Epilog stands out in the at-home EEG monitoring market with its high-precision detection of non-convulsive status epilepticus. Epilog features a gel case for rapid application of an EEG electrode headband that streamlines the monitoring process. Its custom-built 8-channel signal acquisition system processes live data quickly and ensures that caregivers can monitor brain activity effectively and make critical medical decisions confidently. Utilizing a highly sensitive machine learning algorithm, Epilog can detect seizure activity within 25 seconds, enabling real-time monitoring through our user-friendly application. When not in use, the Epilog headband is stored wrapped around this cylindrical case. During the come down of a convulsive seizure, a caretaker will apply gel through this vertical tube, which then radiates through the horizontal tubes that align with the placement of the electrodes on the headband. This simultaneously applies gel to all the electrodes on the band, making it ready for use in under 10 seconds. The location of each hospital-grade cap-gelled electrode on the Epilog headband was determined using standard EEG electrode placements. We found that using 8 working electrodes encircling the head, as well as a reference and ground electrode located below the ears, allows for rapid application of our device, as well as reliable seizure detection. We've minimized the required number of acquisition channels, allowing for comfortable short-term wear. Each electrode is attached to a 3D printed bracket that can be slid along the band and locked into place. This allows for customization of the electrode placements for each child, and the modification of those placements over time as the child's head grows.
Epilog can collect, transmit, and visualize all 8 necessary channels of live EEG data. We've designed Epilog to be fully portable, using Bluetooth for data transmission and rechargeable 9-volt batteries for power. Our custom data acquisition system is designed to collect brain signals in real time, ensuring precise and immediate signal collection. Using active circuit components and software filtering, we separate the brain signal from background noise. Relevant frequencies are then amplified to a detectable range and recorded using our device. We validated the reliability of our EEG system by monitoring intentional blinks, periods with eyes closed, and eye flutters across all channels. Each type of eye movement elicits distinct and identifiable patterns in the EEG signals. By confirming that these produce the expected EEG patterns on the channels shown, we validate our system's capability to capture and differentiate specific and small changes in activity. To quantitatively validate our signal, we calculated the signal-to-noise ratio across 20 trials for 5 users and compared this to average values collected from other wearable EEG systems currently in development. This ratio provides a quantitative measure of signal clarity against background noise, with a greater value being more desirable for sophisticated systems. We needed a method to verify whether these signals were truly from the brain and not simply from other electrophysiological signals that can also originate from the scalp, such as EMG signals from nearby muscle groups. One method to validate brain signal in the frequency space is to observe the Berger effect, where specific brainwave amplitudes decrease when the eyes are open and increase when the eyes are closed, due to the influence of visual stimuli on neural activity. The plot illustrates this phenomenon, with a derived spectral signal-to-noise ratio exceeding 1, confirming the reliability of our EEG system in detecting real changes in brain activity.
To use the EEG signal collected by our headband, we first extracted relevant features. We use the discrete wavelet transform, cousin of the Fourier transform, to convert the data into the wavelet domain and obtain coefficients of key frequency bands, the alpha, beta, delta, and theta waveforms. We then calculated the mean, standard deviation, and power for each of these bands, giving us 12 features per channel calculated in each second. Here's an example of these 4 physiological bands on EEG data collected by our headband. This information is then passed into our balanced random forest classifier, which is a model with class imbalance baked in, which is important for medical datasets like ours. This model predicts the probability of a seizure occurring at any given second for each individual channel, which is then aggregated across our 8 electrodes and thresholded for a final decision. We use the CHB MIT dataset, which has over 3.5 million seconds of pediatric seizure data, to train, validate, and test our model. Different patients were used in each split to ensure the generalizability of our system to the population. Looking at our test set, our classifier reached an ROC score of 0.95, where a score close to 1 is ideal. We also analyzed metrics related to false positives and especially false negatives to ensure that those in a state of status epilepticus are correctly identified. The specificity was 0.88 and the sensitivity was 0.95, consistent with current literature and products on the market today. Additionally, it takes about 27 seconds for the algorithm to reach nearly 100% confidence of a child's state after convulsions have stopped. Delving deeper and looking at each individual patient, we found that those with a regular EEG baseline suffered from a lot of false positives. To remedy this and to ensure that Epilog works for everyone, we implemented fine-tuning, where the weights of the algorithm are calibrated and can be customized to each individual patient. This resulted in improvement on all metrics for all patients. This model is made available to caregivers through a mobile application, available on both iOS and Android. We conducted extensive UI/UX research and user testing to ensure that the app is easy to use in emergency situations. After logging in with their credentials, caregivers are able to see granular information about their child's state and whether they're in status or not. They can also look back and view all seizure history or adapt the ML algorithm by either resetting to the factory baseline model or even fine-tuning and calibrating the model further by recording 10 seconds of baseline neurological data to ensure robust performance at all times.
The market for seizure monitoring devices is rapidly growing and boasts a compound annual growth rate of 4.25%. Our plan to enter this market is to ensure IP protection as we branch out of the pen community to help the 470,000 pediatric epilepsy patients in the US. We have already filed a provisional patent application and are planning to submit a utility patent application in June of this year. Concurrently, we are pursuing FDA 510(k) approval for Epilog as a Class 2 medical device under product codes OMC and OLT for reduced montage standard EEG and advanced quantitative EEG software, respectively. Epilog's real-time, accurate EEG monitoring not only provides precise assessments, but would drastically reduce unnecessary hospital visits by ensuring that only critical cases require admission. This feature could significantly cut hospital costs, with research from Stanford in 2021 showing that detecting status with EEG could save up to $4,000 to $17,000 per patient use. We plan to target hospitals as they would benefit financially and be able to prescribe Epilog to their patients as needed. Additionally, one of our next steps is to conduct human factors testing by seeking feedback from our target population on how to improve the usability of our device. We've been in contact with our mentor at CHOP regarding connecting with pediatric epilepsy patients and testing Epilog in a clinical setting. Epilog is dedicated to reducing the inexcusable 30% mortality rate associated with non-convulsive status epilepticus by providing a reliable at-home monitoring solution. With a powerful lightweight algorithm and a non-invasive wearable, Epilog offers peace of mind, empowering caregivers to make informed, life-saving decisions.